Welcome to our tinyML talk, Neural Networks Frameworks Using Emerging Technology for Screening Diabetic Retinopathy. So we want to say thank you to every of our tinyML strategy partner for committing to take tinyML to the next level together. Analog devices, ion devices, ARM, Deep Light, Edge Impulse, EMSA, PhotoHub, GreenWaves, Gravity, Inc., HOTG, ImageBob, Itemwiz, ClinkerTech, Latent AI, Note AI, NXP, OctoML, Profis, Quexo, Qualcomm, Reality AI, Wixine, Renesas, SAP, Seed, SensiML, Silicon Labs, Sony Solution Corporation, STM, Stream Analyze, Synaptics, SensiML, Syntian, and TDK. Thank you very much. In the moment, we are planning the tinyML EMEA Innovation Forum 2022 in Cyprus. The event will be in person on the October 10th to the 12th. So if you're interested, you can join us. And if you're interested to have a presentation on poster, you can. The call for papers is open in the moment. Our next tinyML trailer brace series will be with Vijay. He's an associate professor in Harvard on the August the 3rd at 8 a.m. on Pacific time. If you're interested to join our community, you can do this at Meetup on the link you see or the QR code or on LinkedIn. Yes, all our videos will be uploaded on YouTube. So you can subscribe our YouTube channel for updates and notification. Our next tinyML talk will be from Arajan about introduction to scale down an open source initiative on Thursday, July the 14th. The webcast will start at 4:30 a.m. Pacific time. I'm really happy that we can have Koteswararao on our talk. He's a recent master graduate from the TU Delft in embedded systems, and he develops software for embedded platforms for autonomous robotic systems. Yeah, so the stage is yours.
Okay. Hi guys, I'm Koteswararao Chilakala. I'm a recent master graduate from TU Delft. I'm here to present my work that I have done in the last 10 to 11 months in the field of emerging technologies, how that can be used for addressing the real world problems. And especially in health, so we have focused completely in healthcare. So one of the applications that we have worked is on diabetic retinopathy. So what is diabetic retinopathy? So retina is a part which is at the back of the eye, and it requires very high-end optics to properly image the part of the eye. Diabetic retinopathy is a disease condition that is developed because of diabetes. So so a normal retina and diabetic retinopathy retina can be identified by looking at certain features as soft exudates, hard exudates, hemorrhages. So these are the number of features that can be identified in a diseased retina. So based on the number of features that are identified in the retinal image, they are graded into five different categories, starting from 0 being no DR to grade 4 of severe DR. This is the standard that is being followed internationally in all the ophthalmology clinics. So what is diabetic retinopathy? Diabetic retinopathy is actually a irreversible condition where as the age progresses, the severity of the disease increases and eventually it results in loss of vision. It's actually a global challenge if you actually look at the incidence that is put before you. There are 145 million people who are actually suffering diabetic retinopathy at the moment, and the projections also show a substantial increase in the number of patients. So most of these patients are actually in the remote areas or low income settings. So inaccessible healthcare is one of the primary cause. So because it's an irreversible condition, we need to early detect and prevent them. So inaccessibility of this medical care is one of the reason that because of the one of the reason for this high incidence. So our goal is to actually create a ultra low power device with high-performing auto-detecting disease detection mechanisms to detect diabetic retinopathy. So most of this, most of the work focuses on how we can actually translate heavy compute to the edge devices so that we can put them in remote areas and then deliver accessible healthcare. So in short, our work actually detected diabetic retinopathy with 90.2 accuracy and provided at least 200x improvement in energy consumption compared to any other conventional hardware implementation. So as I said, diabetic retinopathy is imaged using high-end optics. So there is also evolution happened in fundus cameras. So initially, it used to be a large-sized room, and then the patient interaction will be around 15 minutes to take a proper image. Then later on, they became tabletop devices, and then handheld devices, and then handheld devices with a video camera in it, and then now the optics is so advanced that a mobile phone can actually take a good picture of your retina. So having this advanced optics technology, if this is integrated with high performing auto detection of the diabetic retinopathy models or detection systems, it is a great helpful for us to reduce this global challenge, global disease condition. Typically, from literature-wise, convolutional neural networks have shown some good progress in classifying diabetic retinopathy. So, a typical convolutional layer has stacks some convolutional layers, pooling layers, and activation layers, and then have these have these in batches, connect in various ways, and then try to develop different CNN models, and then try to classify with all the 5 different categories of diabetic retinopathy models. So this is the usual approach, and also successful approach that the researchers followed. And it can also be, as you know, CNNs can be customized to our application. But if you see in the broader perspective, so diabetic retinopathy is very well researched, and a lot of literature is already available, and then high performing results are also recorded. But what we have to see is there are certain downsides, because first thing, most of the results that are provided are either binary classification, whether it is severe or not severe. It's only a binary classification. The other one is multi-level classification, the 5 different categories that we have described. And the other thing that we are focusing in this work is how many hardware implementations that we have seen in this literature. But the major downside is there is a lot of unbalanced data in any data set, publicly available data set that you take. And in a private sector, it is super expensive, because a lot of expertise and trained ophthalmologists are required for you to ophthalmologists and retina specialists are required to grade those images. So there's and with a binary as you can see the results, with a binary classification in the real world scenario, it is either 0 or 1, because there is a lot of unbalanced data. The significance of 1 is largely reduced, and there is some additional requirement of additional information when you actually give out the result that can improve the confidence of the final outcome of the model. That is actually one of the requirement. And again, multi-level classification is still challenging. It's because of very high unbalanced data that we have. And most of this literature survey doesn't focus on model generalizability, because it has to and also doesn't consider some real world scenarios. And as you can see, there is a very limited or no literature that is available when implementing on computational in-memory emerging technologies or on embedded platforms for DR classification. So since there is a little information that we need to incorporate, or as I said, like there is a very need in remote areas, which remote areas this diabetic retinopathy needs to be detected. So we were actually considering how these emerging technologies can be used. As we know, in the current day, with the advancement of AI, the requirement of compute is skyrocketing, and at the same time, the CPU performance is improving exponentially, while the memory performance is actually lagging behind. So there's a lot of gap, and there is a bottleneck. As we all know, that the data movement of from the memory to the processor is a real bottleneck in implementing real-time AI or high compute CNN models. So that's where if you don't have to move the data, so that's where computational in-memory technologies help you or guide you in a right direction in making in efficiently implementing these high compute models. So a typical multiply accumulate operation can be realized as seen in the image by just stacking up the processing elements in a column way in a column, and apply the appropriate inputs and collect the result at the bottom of the column. So this is a very parallel way of implementing this computer architecture, and at the same time, this kind of thing can be scaled up and implemented as a crossbar network to completely realize a vector matrix multiplication that can be seen in the figure B. So a memory wall problem can be easily addressed using these technologies. So in this work, as I said, we are focusing on how we can use these emerging technologies. So the emerging technologies that we have used, that we have focused is using Memristor, that is Memristor device, which is based on resistive random access memory, which is in short, it's a RRAM. It's nothing but a semiconductor device. It's nothing but a semiconductor device with MIM structure, with metal insulator and metal with a metal oxide sandwiched between two electrodes. It's as simple. Its simplicity in this in the structure makes it helpful in manufacturing and scalability. The typical IV characteristics of this device helps or implement or makes this a building block for an entire CIM technology. So the IV characteristics, so this device can be set and reset at two different voltages, and once the voltage, even after the voltage is removed, once the device is reset, even after removing the voltage, applied voltage, the device still retains the memory or the resistance that is induced using resistance reset voltage. Because and it also provides non-volatile properties that provides non-volatile properties of the device. So in this scenario, a small voltage can be used to understand the state by just sensing the amount of current that is resultant from this device. So in that way, this whole thing can be used as a memory and also as a processing element, as shown in the previous crossbar architecture. So these kind of RRAM devices are used to develop a standardized architecture to develop neural network accelerators. So one such architecture is ISAC architecture, as you see in the image. So most of these RRAM devices are implemented in crossbar arrays, and then these crossbar arrays needs extra circuitry, including like DACs, ADCs, and some memory buffers, and all the elements that needs to that is required to make this crossbar work. So in that way, a complete standardized architecture is developed to efficiently translate neural networks onto this CIM technologies. And they also provide a data sheet with data sheet that provides area, power, energy, all the values that are required for us to do performance benchmarking. Currently, this is widely used in academic circles, and there is also some work that is used for commercialization. But we are using this in this work. So overall, what we are doing in this work is we want some model generalizability so that it can handle our detection systems can handle real world noise. And as I said, binary classification is not just sufficient, and multi-label classification suffers because of very high unbalanced data. So we came up with a new labeling scheme. And the next thing that what we have done is, because we are focusing on how we can translate or implement this heavy compute on edge devices, we have done this first of its kind implementation. It's actually a simulation on this RRAM based CIM platform for diabetic retinopathy. And at the same time, because it's a very futuristic or near future technology, we also compared with the existing conventional technology, processor architectures such as CPUs, GPUs, and TPUs. And at the end, like, there is a comparison on how well we can translate and the efficient way to implement a neural network to detect diabetic retinopathy. So, and then a few performance metrics, because there's a lot of benchmarking and performance comparison that we are using. So accuracy and F1 score are majorly used to evaluate models. Latency or runtime and energy. Latency here is the amount of time taken by an image to produce its inference with respect to the hardware platform that is implemented. And energy is also calculated per image. So latency and energy are used to evaluate the implementations on the hardware. So the process that we have followed to achieve this efficient translation onto hardware devices is first data processing, because there's a lot of data, and then it's a very simple pipeline, and also commonly used pipeline: data processing, model training, model evaluation, model compression, and then after the model is compressed, then map those convolutional layers to the hardware efficiently, and then perform benchmarking on various hardware platforms that we are going to consider. In short, so data processing is very much required. The novelty or the innovation that what we have came up with is, we have collected all the public data sets and then randomized and mixed them such that we actually took three levels of data sets: a small data set, and in any of the data set, we made sure that the least number of images that in corresponding to that category, the higher is not less than 10% of highest number of images that are available in that data set. So in that way, we have tried to address this unbalanced images scenario. And then we also wanted to understand how these models behave with small data sets, medium data sets, and large data sets. It's especially because we could actually have like small data sets and then show some very good results with higher epochs and tuning the hyperparameters. Similarly with medium and large. So there is a very good comparison that we have performed. And when we are trying to do this implementations and CNN trainings, we actually need to use data augmentations by resizing, rotating. These are usual concepts that we usually do while training a model. And besides that, so in this work, we only focused on two networks. These are because these are very well established and widely used in the literatures, and very widely quoted, very well performing and contrasting model architectures. The first one is Inception v3, and the second one is DenseNet 1-to-1. Inception v3, it has like asymmetric combination of factorized kernel filters, so that makes it so unique. And then it is very helpful for large data sets. And at the same time, for DenseNet 1-to-1, it is actually a stack of all the layers that are required for implementing a convolutional layer. But what makes it unique is how the layers are connected, how it's not a sequential one, and then the top layers are very much close to the bottom layers. So that kind of connection is completely unique from Inception v3. So that diversity, we wanted to understand how these models work. And then we followed a typical model training process. So we have considered all the we have performed a grid search by considering at least 3 or 4 hyperparameters, say regularization parameter, this momentum, and and a number of epochs, and adjusting the hidden layers. So there are multiple hyperparameters that we have considered, and then use this grid search to, and also especially learning rate, used to understand how what's the best that we can get out of the model, and in combination with a particular data set. And then the manual tuning, and it's completely a manual tuning process. So it's completely typical. If there is there is, first we consider high training error, training loss and validation loss, and then if they are not satisfactory, we perform certain changes accordingly, and then we again train the model. And then the next thing that we that we stressed on is how what is the outcome, or what is the outcome that the person, the end consumer, so that end consumer will actually see and also feel confident about using the product. So it's not just a binary classification or multi-level classification saying what's the severity. So what we understood is, so multi-level classification has certain drawbacks, but binary level classification has higher accuracy values. But because it's completely unbalanced, if you have a 1, so the confidence on what the result that you see might go low. So that's why we are having a severity score. And at the same time, with this binary score, we are also having an exclusivity index, which shows that, okay, if you are 0 in this, if you are 0, and then if the exclusivity index is also 0, you are completely normal. And then if you are 0 and if your exclusivity index is 1, then there is mild or like some features that pertain to DR is identified, and it goes on. But majorly, this is calculated based on the softmax probabilities that we obtain when we perform multi-level classification. This is majorly because there is the major drawback that we see in multi-level classification is marginal mismatch or marginal misclassification. So to address that, we came up with this simple algorithm. So if you see in the example, the ground truth is actually true, 2, but the softmax probabilities show that the predicted label is 1. But based on the algorithm that we detected, it gave a severity label of 1, 0, and 0.57. So 1 itself says that you have diabetic retinopathy, and 0 says that the diabetic retinopathy is present, but the diabetic retinopathy is not too severe, and that can be cross-checked with the severity score, which is 0.57, which is nothing but the addition of all the softmax probabilities of category 2, 3, and 4, because these are considered as diseased or like immediately needs immediate attention. So that's so it not only gives extra information to the user, but also addresses the marginal misclassification that is present in a multi-level classification. And the next thing, after we have like good accuracies and we have good performing values, so eventually when we are going to hardware, we try to see how well we can compress and then translate that into translate that onto the hardware. The typical techniques that we followed are quantization and pruning. We have only followed low magnitude pruning, which is unstructured pruning. So pruning is nothing but if once the model is trained, and then if the value based on a threshold value, if the weights of these certain neurons or certain nodes are less, or based on the values of the weights of certain nodes when compared with the threshold, it will be present or it will be absent in the in the resultant network. In that way, you can reduce certain computation complexity, and also it can and also reduces the certain computational complexity. And at the same time, once it's pruned, so we try to explore if any quantization technique can be used to reduce the size of the model, and also reduce the size of the model, and also see what its impact on the latency and energy values. So the algorithm that what we followed here is we only quantized convolutional layer. We didn't quantize activation layer. It's because the later results are way worse if you quantize activation layer. And so once the quantization layer, convolution layer is quantized, and then the typical convolution happens, and the accumulator or the activation layer performs at the usual float point or the maximum that the processor or the microcontroller offers, and then again they are requantized to feed to the subsequent layers. So these are the methods that we followed, and then these are the techniques and these are the methods that we wanted to implement, and for this benchmarking, and also see how efficiently we can translate neural networks onto the hardware, see how they perform on the different hardware systems. So that's why for comparing in a better way, we have performed all the executions on CPUs and GPUs, and also a mobile processor which is based on which is Google Coral board, which is a TPU processor, and the eventual emerging technology that we were talking about based on RRAM. Based on the ISAC architecture and the dataset that we have simulated our own simulator to give energy profiling and latency profiling values. For energy profiling on CPU, we used STU command line, and for energy profiling on GPU, we used NVIDIA SMI command line tool. And as you know, we have considered 3 different sets of datasets, but exclusively we have used a Mesidor 2 dataset on only for evaluating the model, final evaluation of the model. It is not used in training, validation, and test, but final evaluation and comparison of the model is only made on Mesidor 2 dataset. This is a glimpse of how the simulator works in providing the energy profiling for ISAC architecture. As I said, there are many other circuitry elements and also crossbars which are developed using RRAM devices. First, we need to understand what kind of matrix vector multiplication, the size of matrix vector multiplication that we are trying to implement, that we are trying to use, and then based on that, we find we interpolate how many circuitry elements or individual elements that are described in ISAC architecture are needed to perform that particular operation, to run one particular operation of that convolutional layer, and their corresponding energy power values are provided in the datasheet. So to complete execution, we need 3 cycles. where at different stages, different circuit elements get activated. And then eventually in each cycle, what circuit elements are activated and their powers are accumulated. And eventually we calculate this total energy consumption. So this is only for one convolutional 2D convolutional layer in Inception v3, this calculation shows. Similarly, this is done for latency and also DenseNet. Once we manually calculate for one layer, that based on the network architecture, we try to come up with a model so that it calculates the total energy consumption in registering one image. So eventually, moving on to the results. So we wanted to see first multi-class accuracy, how well our models are performing, because even the severity label is classified, is built on softmax probabilities that are generated in multi-class accuracy. So here, as you know, I have small, medium, and large data sets, and you see the results that I have got for both Inception v3 and DenseNet. The accuracies for when trained on small data sets are much higher when compared to large and medium data sets. So that is a very interesting observation. It's not actually an interesting observation. That's the final, that's the outcome. But whereas if you actually see the confusion matrix for the test set, that is for the test set that is evaluated with a model which is trained using large data sets. So we can clearly see that 0 category, 2 category, and 4 category are able to are categorized significantly well, but the marginal classification is the drawback, or is the cause of problem, which results in lesser accuracies or lesser performance metrics. But so as we said, severity label will address this solution, which after performing severity label, after calculating severity labels, which is just 0 and 1, and then which is based on a binary classification, all the performance metrics are really shooted up, but that is that is expected, because this is only a binary classification and all the performance metrics are on binary classification. But the true utility of the severity label can be seen in this histogram that is plotted again, which is again plotted for the test set, which for the large test set, and which is and the model that is used to evaluate this is trained using large data set. So what we could see is all the zeros and ones are going into the proper. So what we could see here is there are very less false negatives, as except the there are very less false negatives, which is very crucial for any medical device. Except in this histogram, except the category 2, which is misclassified as category 0, and that too in a very lower proportion when compared to all the images that only category 2 is misclassified, which is only of lesser number. So the false negatives or the previous confusion matrix that you have seen, there is a tremendous increase in how we communicate the outcome of the model to the end user. So end user, it's not just binary, but it also gives extra information how much severity that you have. So finally, we land on model evaluation, because we have tested on training test data sets so far, and then we have got some good performance metrics. But the real challenge for any model is on model evaluation. So, which is completely alienated the data set, the Mesidor2 data set that we have used is completely alienated in training, testing, and validation or tuning of the models. So here, when we tested this, as you can see, the models which are trained on large data sets completely outperformed or like maintained consistency for their previous performances and for their previous performances, and the models which are trained on small data sets completely failed or have shown very negative performance metrics when compared to the other results that we are seeing. So what we could actually conclude from this is the large data sets, though it has several issues and like marginal misclassification or some imbalance in the data, but eventually it is actually learning all the real world noise and it is consistent than the models which are trained on the small data sets. So that is something initially we can judge that, okay, small data set models which are trained on small data sets are performing well, we can go with that. But the actual truth, when we evaluate with this different scheme of model evaluation, we could see clear distinction of the size of data set that we need to use for a reliable model to be deployed. And at the same time, it is quite clear when between the performances of multi-classification is little of severity label is very higher than performance of models which are trained for performance metrics which are shown for multi-class classification. So moving ahead, all the implementations are only for models which are trained on large data sets, whether it is Inception V3 or DenseNet 121. Now we have this high performing or whatever performance that we can extract from these models. We have this good models which can be deployed with some reliability and some with good performance. Now we wanted to see how well we can translate that into hardware. So first thing what we have done is using pruning. So pruning, the percentage of pruning doesn't seem to change much. The performance doesn't seem to decrease or increase with the increase in percentage of pruning. That is a good sign. But this pruning cannot be completely exploited because it needs because we have performed unstructured pruning. It needs dedicated or appropriate hardware so that we can maximize the utility of the pruning that we have performed. But it is good to know that with the increase in pruning percentage, we didn't see any drop in the performance of the models, and also the model size of the models reduced because that is completely expected, because a lot of the model becomes completely sparse. And the next thing moving forward, which is very important, the quantization schemes that we need to be aware when we are translating our model, our high performing models onto hardware. So as I said, we can there are two layers in a typical CNN implementation. You have a convolution layer and then followed by an activation layer, max pooling and activation layer. But activation layer is a kind of an accumulator, and then you can quantize the convolution layer, but the convolutions that are performed after quantization results requires higher bit of values to preserve that to preserve the result of the product, to preserve the result of the convolution that we have performed, and try to propagate that to the next layer. So that's why any quantization on activation didn't show any good results. most of the aggressive quantization for weights or the values in the convolutional layers or the nodes didn't seem to affect or maintained accuracy when compared to the baseline. Baseline here is with float 32. So float 32. So when implemented on float 32, which is our baseline, and the maximum performance that we extracted, and even after 4-bit quantization that we have performed, and with activation performing at float 32, most of the accuracies are maintained when comparable to the baseline accuracy. And again, the latency values. As we know, RRAM has around 300 nanosecond cycle requires only very minimal or switching time or operation frequency, very high. It can operate at very high operation frequency. So hence we have got we have got around 0.29 milliseconds to process one complete image, which is like giving out a prediction. So because it's too low, the images that I have shown are compared with the value of RRAM. So you can see that at least because GPU is again a parallel unit, which is kind of a parallelism that we could see in CIM architecture, and there is less data movement in CIM architectures, emerging technologies. So that's why you could see 28x improvement on GPU's performance and 130x improvement on CPU's performance, and almost 5,000 or like 5K improvement or very huge improvement when compared to the mobile processors or the TPUs that we have used, Google CorelDAO board that we have used. And coming to the energy consumption, it is again at least you have around 200x improvement in energy efficiency when implemented on RRAM, irrespective of when compared to any other platform. So we could actually see, but besides comparing with RRAM or the emerging technologies, we could also see how these single board computers can be the state of the art single board computers, and its impact and its addition to implement these heavy compute models in the remote areas to calculate the values. So we could actually see those values here. And so in that way, we could also take a very informed decision while designing these systems, whether it is on CPU, on GPU, or on TPUs, on TPUs. And similarly, in energy consumption, we have 200x improvement, and if you keep the RRAM aside, the trend is still the same. We have GPU the lowest, CPU the next, and then mTPU the mobile processor the third. It's in this ascending order. This is kind of first of its kind implementation that we have performed for diabetic retinopathy application on various platforms. So this gives us an informed information or actual values while deploying reliable models that can be used and used consistently with the in the remote areas. Yeah, and then the final thing is because it's RRAM and it's completely theoretical, it's a simulation based thing. It's obvious that as we move from float 32 to 4-bit quantization, the amount of energy or the hardware that is required to implement those structures or the models decrease exponentially. But the main takeaway is the accuracy is not lost when compared with the baseline. So 4-bit quantization can be used especially when on edge devices, or if you require less memory space. So that's that's some information when you are translating it onto a neural network on the hardware. Yeah, I mean, that's from my end. So we have actually seen how to tackle real world noise, and then how large data sets can heavily show us consistent results and see through consistent results. And we also how smaller data sets affect the initial premise of how good the model is, and what is the necessity of large data set. And the new labeling scheme, it actually provides more information, very informed decision that even the user can take, which is very much required in remote areas when compared to binary classification or just giving out a number, okay, it's severe or not. Extra information is useful. And with the new labeling scheme, we got around 90%, which is which can be used, which can be deployed, which can be deployed, and which can be improved further. Yeah, and then we have explored emerging technologies based on RRAM and some CIM architectures. How these high-performing neural networks, when combined with these emerging technologies, what are the challenges and what are the new ways that we could found, and what are the improvements that we need to implement. So that's something first of its kind that we try to document it with benchmarking. And again, the final thing, how well we could translate, how if we implement that with current state of the art, what is the state or what is the stage that we will be in when implemented with offline in on any of the processors, any of the conventional processors. And we have also recorded the latency and energy improvements with between conventional processors and emerging technologies. So there's a very so the way forward, or the bottleneck, or the new paradigm that we are leaning towards seems to be promising, for especially for AI artificial intelligence and based applications, where we can generate very good neural network accelerators. And with this, I like to thank my supervisors, Stephen Wong, Associate Professor Rajendra Bishnoi, and Sumit, who is my everyday mentor. And so this whole work that is presented to you comes under QCE group at TU Delft, and the focus group that we have that we are working under the supervisors that are majorly focusing on emerging technologies and also and their applications into healthcare. So with this, I thank the organizers for giving me this opportunity.
Great, thank you very much for your talk. So now we have some questions. Let's go through the question. So one of the first question is, what is the minimum resolution of camera which can be sufficient for DR detection?
Excuse me?
So what is the minimum resolution of camera which can suffice for the DR detection? Yeah,
so a high-end full HD image should do the job. Full HD image. At least it should be a full HD image. That is because there are many micro features. The features that we wanted to identify are only contribute to 1% area of the whole image. So at least I would recommend, while capturing with a full HD, then you can downscale it and use it for further model development.
Okay, great, thank you. Then the next question: how many bits you used for RRAM cell in the simulation?
Which one?
How many bits you used for the RRAM?
I didn't get the last part. How many bits I used for?
For the RAM, for the RAM in the simulation.
Okay, for the RRAM. Okay, it's 2 bits.
2 bits. Okay.
2 bits.
Good. And then have you evaluated other neural networks such as spiking neural networks?
That is, yeah, definitely. But I'm not sure about how, what will be the performance of those spiking neural networks, especially in giving good performance metrics. That is not explored, but that is one good way, especially for if you want to implement it on emerging technologies. So that is a very new area of research.
Okay, thank you. Then the last 2 questions. Did you know how much % you reduced the model size?
How much % I have reduced the model size?
Yes.
Model size. So it depends on the pruning and as well as the quantization. The percentage of because I haven't used pruning because it's only low magnitude pruning. We can use structured pruning to efficiently translate that into hardware. Because I have done unstructured pruning, so I didn't get any benefit in reducing the model size when transferring it into the hardware. But with quantization, I reduced it by 4 times. That's it.
Okay, thank you very much. And then the last question. There are other faster NVMs with lower power than RRAM. Did you have any particular reason why you choose RRAM? And can this be implemented on other NVMs like MRAM? MRAM.
NRAM. Okay, I'm completely unaware of that NRAM thing, but this is a very new topic for me as well. So I'm just exploring this. So I couldn't give much information for your question.
Okay, thank you very much. Good. Yeah, then thank you very much for your presentation. It was really interesting and there was a lot of questions. So let's, in the end, we want to say thank you for the tinyML strategy partners. We want to say thank you to the executive strategy partners like ARM AI, the latest in AI trends technology and best practice from ARM and in our ecosystem. Then EdgeImpulse, the leading development platform for HTML. Then Qualcomm AI research for advancing AI research to make efficient AI. Then Cynthian making Edge AI a reality. We want to say thank you to a Platinum strategy partner like DeepLight, the fastest video analytics solution on ARM CPUs. Clinker Tech for global AI solutions. Then Reality AI, the high value or safety critical use cases. Then Renesas is enabling the next generation of AI-powered solutions. Sony Semiconductor Solutions Corporation. Our gold strategy partner like analog devices, where what if becomes what it is. Then PhotoHub making over-the-air film and machine learning models updated, simple, and accessible. Then Latent AI, the easy button for developers. And NXP, together we can accelerate breakthroughs that advance our world. Seed Studio to deploy tinyML model into real world, plug and play. And SensiML for analytics toolkit suits. ST Microelectronics provides extensive solution to make tiny machine learning easy. And Synaptic Engineering exceptional and experience. SensiML, which builds sensing and inference hardware for ultra-low power devices. And our silver strategy partner like RN devices, EMSA, Greenwaves, Gravity, HOTG, Image, Bob, Intimus, Note AI, OctML, Profis, Quixo, Xen, SAP, Silicon Labs, Stream Analyze, and TDK. Thank you very much. So yeah, our next TinyML talk will be on Thursday, July the 14th from RRAM, which introduced to scale down an open source initiative. If you're interested to hold your own talk, please contact me or talks@tinyml.org. And yeah, thank you everybody for joining the talk. And if you're interested, you can stay in the room and we can chat a little bit, or if you had further questions. Yes, thank you very much.